In this lesson series, we're going to begin looking at the bipolar junction differential pair, which is an important building block for most amplifiers, at least operational amplifiers or amplifiers that have a differential input. And we've actually seen the makings of a differential pair already when we looked at some of the useful pairings at the end of Chapter 7, where we looked at some building blocks for IC fabrication. We saw that if we combined a common collector stage with a common base stage, we arrived at an amplifier that had some interesting characteristics. And we will return to that now and look at this pairing in more detail and define it, rename it, I guess, as a differential pair. So I have some notes that are already written here. Instead of writing the notes out as I go, at least initially here, I'm going to just talk through them. So pause the video if you need to study the notes that are on the screen, as I will move probably faster through the notes than you're able to either absorb or write them down. So a differential pair is created by cascading a common collector or a common drain stage with a common base or common gate stage, and then combining the two parallel biasing sources, the current sources in the source or emitter legs of each of those transistors, and then optionally replacing the grounded base of the common base amplifier with a second input, VI2. And this yields a differential input. So, and then lastly, we can add a collector resistor to the common collector stage, which allows for an optional differential output. So these three schematics kind of walk you through that. So here is a common collector stage. There's no need for a pull-up resistor or a collector resistor at this point. It has a biasing current I1, and the output is taken at the emitter. The output of the common collector stage feeds the input of the common base stage, and so that's connected to the emitter of Q2. Q2 is biased with a current source I2, and the output for a common base stage is the collector, which is tied high through a resistor RC. We combine the current sources, no need to have two of them, so we just have one current source called I, and this is the beginning of a differential pair. It's actually, in this case, a differential pair that is configured to have a single-ended, what we call a single-ended input, and a single-ended output. But then, if we move on to this last configuration here, we've added a resistor RC to the collector of Q1, and we have lifted the base of Q2 and define that as an input VI2. Additionally, with the addition of the collector resistor on Q1, we've identified another output terminal, and that is VC1. So we have VC1 and VC2 as outputs, and we have VI1 and VI2 as inputs. And this is this has full symmetry. You notice that you could consider either amplifier stage as the common collector amplifier stage or the common base stage. So let's go back to the first view here, where we're looking at the common collector stage and common base stage, and let's recall some of the characteristics of each of these stages. So the common collector stage has a low voltage gain. Typically it's approximately 1. It might be a little less than 1, depending on what we load it with, but never greater than 1. It has an input resistance that is relatively high. Certainly it increases. The resistance seen at the input is beta plus 1 higher than the load resistance, whatever we connect out. Let's say right out here, if this was where, if we weren't driving a second amplifier stage and we just had a resistor, load resistor, we would be buffering our source, VI, from our load by a factor of beta plus 1. So we have a pretty decently high input resistance, and the output resistance is low. And this is what's characteristic of the common collector, a unity gain and a low output resistance. So whatever resistance would be driving the input of the amplifier here would be R sig, coming from our signal source. When we look back into the output of a common collector amplifier, we don't see R sig, but we see R sig divided by beta plus 1. Now, we also see the incremental or dynamic resistance of the emitter, but that's low as well. So the common collector stage provides a low output resistance, high input resistance, and a gain of 1 or a little bit less. The common base stage provides a high voltage gain. It has a low input resistance. So notice that the output resistance of our common collector stage, which is low, is well matched with the low input resistance of our common base stage. Recall that when you have two amplifiers, let's say if we go back to chapter 1 material here where we have two amplifiers and they're characterized by a voltage gain, an output resistance, and an input resistance, that this RO1 and RI2 form a voltage divider. So whatever this voltage is here coming out of this source, call it VO1. The voltage here going into the second stage, call it VI2, is going to be equal to VO1 times this voltage division, Rn2 over Rn2 plus RO1. So it's important that we have a low output resistance to our first stage because the input resistance of the second stage is a low resistance. And so we have good matching here. That's a good pairing. And then lastly, the output resistance of the common base is moderate or high. Okay, so overall what we have is we have relatively high input resistance, a high output resistance, and a high voltage gain. And you might ask, well, wait, isn't that what we had with just a common emitter amplifier? Because a common emitter amplifier had decently high input resistance, it had a high output resistance, and high voltage gain. And the answer is, well, yes, those are similar. I mean, those are the same those three characteristics are essentially the same, but there are some differences. A major difference with the differential pair is that the quiescent operating point for this amplifier stage is Vi equal to 0. Or more specifically, it is Vi Vi1 equal to Vi2. So if we look at this fully differential version where we have a Vi1 and Vi2, the quiescent operating point is when those two voltages are the same. So if you ground Vi2, then the quiescent point for Vi1 is 0 volts. And we've never seen that before. In all of our other amplifier configurations, the input always had to be at some bias voltage, some DC voltage. Now we did overcome that DC offset by adding a decoupling capacitor, and then we could have maybe some resistor divider to set a bias voltage to our gate or our base. But we were then AC coupled. We couldn't be DC coupled. And recall that one of the motivations for looking at the differential pair is that in IC fabrication you can't have large capacitors on the IC. And so you actually want to design an amplifier as much as possible being DC coupled, not AC coupled. until you get off the IC, and then in the circuit, discrete-wise, you can add capacitors thereafter. Now, the differential pair has much more to offer than just the ability to avoid having a large input DC or AC coupling capacitor. Again, it actually affords you the ability to have a DC coupled amplifier that has a bias point or quiescent point of 0 volts at the input. Furthermore, because it's a differential pair, it gives you the ability to, or gives you a hook, if you will, to implement feedback. So remember op-amps. An op-amp has an inverting and a non-inverting input, and the output is essentially the product of the difference between those two inputs. Well, what we see here in a differential pair is essentially an op-amp function. We will see that in the end, the output voltage of a differential pair is some quantity, some gain, times the difference between VI1 and VI2. And so what that allows one to do is we can now, let's say this stage is the front end stage of a multi-stage amplifier. And at the end of that multiple stages of amplifiers where we have both lots of voltage gain and maybe then the final stage is a common collector stage where we're trying to deliver a lot of current from the output, or otherwise put, we want a low output resistance. We take the output and we're now able to feed the output back to VI2, say. And so we're able, and we can even feed it back through a voltage divider resistor network. And we have the makings of an op-amp. And in fact, that's how an op-amp is designed. It begins with a differential pair at the input. Okay, so let's go into the analysis some. And we're going to first do this at the large signal, and then we'll look at the small signal. So here we have the fully symmetric differential pair with VI1 and VI2 inputs and VC1 and VC2 outputs. And we're going to actually solve this in the large signal, and so this is not linear in any way at this point, but we'll get to linearizing it. So first we want to note that if VI1 is equal to VI2, then the VBE1 is equal to VB2. In fact, we don't even have to say that VI1, VI2 is VI1 equal VI2 equal to 0. If they were both equal to 1 volt, or whatever voltage, we would still say by KVL, just do KVL around the loop involving the base emitter junction of both Q1 and Q2 and the two voltages VI1 and VI2. And you'll see that VB1 is equal to VB2. These transistors are matched. So if they're matched and they have the same base emitter voltage, then we can say that I1 is equal to, or IE1 is equal to IE2. The two emitter currents are equal. And since IE1 plus IE2 is equal to I, then we can say that each current, IE1 and IE2, at their operating point will be equal to just I over 2. So this establishes the quiescent operating point. Now this will be necessary eventually when we do the small signal analysis and we want to calculate the GM for each transistor. The thing to remember is that if I is 1 milliamp, then the current going through each transistor that will be involved in computing the GM will be a half a milliamp. Right? So the GM will be would be something on the order of 25 millivolts, or sorry, half a milliamp divided by 25 millivolts. I over VT, or I over 2 divided by VT. Okay, so the first thing we want to write here, we'll start with this. I've got this number in here to kind of walk us through the analysis. First, we want to just write the Shockley relationship relating our emitter current of Q1 to our base emitter voltage of Q1. Now I've labeled the emitter voltage VE because it's common to both. So we would have IS And because it's emitter current and not collector current, remember the relationship between collector and emitter current is the alpha term, which alpha is beta over beta plus 1. So it's about 1. So that's a very small term here. IE1 is then IS scaling current over alpha times the exponential e to the VI1 minus VE, so that's the VBE junction voltage of Q1 divided by V thermal. And we can say make a similar statement for IE2, but it involves VI2 instead of VI1. Next, we can go up here to 3, where we now take the ratio of these two currents. When we take the ratio, the IS over alpha cancels out, and the VE is eliminated as well, because now the exponents are going to be subtracted. And we're left with IE1 divided by IE2 is equal to e to the VI1 minus VI2 all over V thermal. So we use this third expression here, along with this fourth expression, which is just KCL at the summing node of the two emitters, where we see that IE1 plus IE2 is equal to I. And using 3 and 4, we can solve for IE2 and IE1. And here we find that IE2 and IE1 are as follows. IE2 is I divided by 1 plus the exponential e to the VI1 minus VI2 all over V thermal. So let's go on to the next page, and we recap this now, where I have replaced VI1 minus VI2 with what I'm calling VID. D is for differential, or the difference. All right, so it's the difference of the two inputs. This, if you recall, for an op-amp, remember we define the output of an op-amp, VO is the gain, A times delta V, where delta V was the difference between the non-inverting and the inverting input of the op-amp. Well, VID here is that delta V. Now let's plot this in the large signal versus VID. Our quiescent point is going to be VID is equal to 0, and at that point we have each transistor is carrying half of the total current. And what will actually happen is as you increase positively VID, that means you're going to raise VI1 and decrease VI2, or hold VI2 constant. Then what will happen is you will enhance Q1 and you will starve Q2. And that is evident here by seeing that as we increase VID, IE1 goes up and IE2 goes down. And IE2 will go down ultimately to 0. We'll starve it off. And if you get very far away from 0 volts, soon enough, all of the biasing current I will be flowing through IE1, through Q1. Go the other way, and the opposite will happen. And so what we really have is, if we go back to the circuit, you have this current source I, and that current I gets steered either through Q1 or through Q2, or at the quiescent point equally between both, based on the differential voltage between VI1 and VI2. So it's a current steering circuit. It's a voltage-controlled current steering circuit, and it's highly sensitive. You can imagine that. Go back down here where I have a little room. We have two diodes, the two VBE junctions. Okay, and if this is my differential voltage, VID, you can imagine that it's not going to take too much voltage to fully turn one of those off. If those diodes turn on at 0.7 volts or around 0.7, then, and if they don't really increase much above 0.7 because of the high conductivity of the transistor, then by the time we get to 0.75 volts, let's say, we would expect that one of the diodes would be fully on and the other one would be fully off. Right? And of course that, I should add in here, we've got this current source I that's flowing this way. So what that means is you've steered all of I through the one diode and none of it is coming through the other diode. So the scale, the horizontal scale here may be that this is like 0.7 volts and this is minus 0.7 volts. I don't know, but it's on that order of magnitude. It's not a big voltage difference. Now how does this affect the actual voltage at the output, that is VC1 and VC2? That's pretty straightforward to calculate that. We have that VC1 is simply VCC minus the current IE1, and I really should have an alpha in here to transfer it up to the collector, times RC. And so we'll have a voltage transfer characteristic that will look very much like the current transfer characteristic. At 0 volts, the current, or the resting or quiescent voltage for VC1 and VC2 will be this VCC minus RC times half of the bias current times alpha. And then as VID increases or decreases, we're going to be, that voltage will be moving up or down, and the rate at which it moves up and down is going to be a function of RC. And so here I have, for a very small RC, we might expect something like I've plotted here. For a larger RC, which is what we would typically see, the slope is going to be much steeper, and will actually cause either the transistor to go into cutoff, or it will saturate, or not saturate, it'll go into the triode region. And here we see VCE sat. So if, for instance, if the VID goes too much negative, not very far, then VCE2 falls all the way to a voltage of VCE sat approximately. And so that means that Q2 would be in the triode region, or it would be in the, let me be careful here, it would be saturated, yes, since it's bipolar. It would be saturated, and Q1 would be in the cutoff region. Now we're ready to look at the small signal behavior. Now we could go back to this circuit right here, and we could draw a small signal equivalent. And we might do that in a subsequent lesson, or maybe even later on in this lesson. But for the time being, we're going to take the large signal results, which are right here, and we're simply going to linearize those equations. And that will lead us to small signal behavior. So here's how we're going to do that. We're going to linearize the exponential term e to the VID over V thermal. Recall that that shows up in the denominator right here for both of our currents. So we take a Taylor series, and we're just going to take the first two terms. And here I'm considering the case both for when we have e to the plus VID over VT and e to the minus VID over VT. And if we take just the first two terms, we get 1 plus, or it'd be minus, times the exponent value, which is VI over VT. And recall the second term would be a 1/2, and then you'd have the exponent term squared and so forth. But we're just taking the first two terms. So now we plug that into our expression for IE2, which we have right here. We combine the 1, so we get I over 2 plus 1 over V thermal times VID. Now this is still a nonlinear expression, but now we can more readily take the derivative, or the partial, of this current with respect to VID. So now what we're really doing is we're really looking for, if I go back to this transfer characteristic right here, we're looking to calculate the slope right in this region here. And what we've done is we've taken advantage of the fact that around 0 we can approximate the exponential as a 1 plus VID over V thermal. And so now we're going to take the partial right here, and it's important we're going to evaluate it at VID equal to 0. So we're going to evaluate it at that operating point, which is where it's 0. Now think ahead now, or think back to op amps. Remember how we have, if the voltage gain of an op amp is infinite, then we have that ideal op amp rule that says that as long as there's infinite open loop gain and there's negative feedback, we can say that V, the non-inverting input, is equal to the inverting input voltage. In other words, that delta V, the difference between the two, is equal to 0. And that actually is quite true. Now, it may be off by some microvolts, but it's very small. And so it is not unrealistic that in a real amplifier that uses a differential pair, that even over a very large output voltage swing of that amplifier, if you look at the VID, the delta V at the input of the differential stage, that voltage will never get very far away from 0. And so it is quite appropriate that we do this linearization about the VID equal to 0. So anyway, you take the derivative of that, which we've done here, and once we plug in the fact that VID is equal to 0, this expression simplifies, and we end up with a simple relationship here, that the small signal or incremental emitter current in Q2 is equal to minus I over 4VT times the differential voltage VID. And so I've redrawn here just to point out what we've calculated. Essentially, that's the large signal response there, but right around the operating point or the quiescent point of 0 volts VID, the slope of those curves are equal to minus I over 4VT and plus I over 4VT. We can now take this result and we can look at what the small signal voltage gain or small signal voltage response at the collector is. And here we have VCE2, and that's simply going to be equal to minus RC times IE2 times alpha, because we're reflecting IE to the collector. And then we substitute in our value for IE2, and we arrive at VCE2 is equal to alpha times, it would be RC times I over 2, which that's the quiescent current times RC, so that's actually the quiescent voltage drop across the RC, so that's why I've written it in its final form as capital VRC divided by the thermal voltage, and then all of that times VID over 2. And we can arrive at the same result for VCE1, except that there's a minus sign now. So if we consider the symmetric output differential stage, where we have a VC1 and a VC2, and we take the output across those two, we can define that as VOD. Okay, we define VOD, output differential, is equal to, and here I've written it as VCE2 minus VCE1. We could have defined it the other way, but I like it this way because it's going to give an overall gain that's positive rather than negative. When you take these two terms here, put those together, or plug those into here, we end up with an output differential voltage that is equal to little VID, the differential input, times the voltage ratio, capital VRC, over the thermal voltage VT. So it's a very simple result. And again, we're seeing this behavior where it's either collector side voltage divided by emitter side voltage, or impedance, collector impedance over emitter impedance. Now, lastly here, I'm going to show just a couple different configurations that all operate basically the same, but they have a little bit of variation in their input format and output format. So firstly, here on the left, we have a differential input, differential output difference amplifier. The symbol for that looks like an op-amp. It's got two inputs, it's got two outputs. Put a little circle here on the lower output to show that it's inverting. And so the input is VID and the output is VOD. And I'm showing the gain as being what we computed, capital VRC over V thermal. Now we could decide we don't need to take the output differentially. We want to just take the output from the collector of Q2. So here we have V out. We could still leave a resistor over here on Q1, but we could also remove it. It wouldn't change the behavior of the circuit. Without it, we'll have a little more power dissipation in Q1, but the overall power dissipation of the circuit won't change at all. This is called a differential input, single-ended output. And here's the schematic for it. And then lastly, we could do a single-ended input, single-ended output amplifier. And to do that, we would tie VI2 input to ground, and we would apply our input just at the base of Q1. And here the voltage gain will be just like it is for the differential input, but single-ended output. It'll be capital VRC over 2 divided by the thermal voltage. Okay, so there's a first view of the differential amplifier. I'll stop at this point and we'll pick up with a subsequent lesson where maybe we'll draw the small signal model for this amplifier stage, and then we'll start solving some problems with it and eventually combine it with some other stages to produce a more useful overall multi-stage amplifier functionality.